Hello everyone, I am Dr. VRAO. We have been discussing the chapter Chemical Equilibrium. From the lecture 31 and 32, we came to know that equilibrium is established in reversible reactions carried out in a closed vessel, and we came to know that equilibrium constant, its units, relation between Kp, Kc and Kx, right, and factors influencing the equilibrium constant. These are the concepts that we had gone through from lecture 31 and 32. Now we shall go through the characteristics of equilibrium and equilibrium constant, right? Equilibrium and equilibrium constant. Equilibrium and equilibrium constant, right? Equilibrium is a state that established in reversible reactions, we know that. Therefore, equilibrium is a state where the rate of forward reaction is equal to rate of backward reaction, right? So, equilibrium is the state where rate of forward reaction is equal to rate of backward reaction, and we can define the equilibrium in another with another definition. Equilibrium is the state where the concentration of products, concentration of reactants does not undergo change with time, right? So, the concentration of reactants and products does not undergo change with time, right? So, these two conclusions or these two statements we can represent these two statements with a diagram or a plot. For example, if you plot a graph between time versus rate of reaction, if you plot a graph between rate of reaction versus time, that is rate of reaction on ordinate and time on abscissa. So, the rate of that equilibrium is a state where the rate of forward reaction is equal to rate of backward reaction, and with increasing the time, rate of forward reaction goes on decreases and rate of backward reaction goes on increases, right? So, the rate of forward reaction goes on decreasing and rate of backward reaction goes on increasing, and equilibrium, the state when the equilibrium is established, the rate of forward reaction and rate of backward reaction becomes equal at equilibrium. So, this single line indicates the equilibrium that established in reversible reactions. So, with increasing the time, the rate of forward reaction goes on decreasing, and with increasing the time, rate of backward reaction goes on increasing, and at the when the equilibrium is established, rate of forward reaction is equal to rate of backward reaction, and we can represent the equilibrium with another plot, that is, if you plot the graph between time and concentration on ordinate and time on abscissa. So, the concentration of reactants goes on decreasing and the concentration of products goes on increasing, right, with increasing the time. So, during the course of time, the concentration of reactants goes on decreasing and the concentration of reactants goes on decreasing, right. So, the concentration of reactants goes on decreasing and the concentration of products goes on increasing, right, goes on increasing. So, when the equilibrium is established, this is the forward reaction in which the concentration of reactants goes on decreasing, and this is the backward reaction in which rate of that is concentration of products goes on increasing, and that equilibrium, this is the equilibrium, and at the equilibrium the concentration of reactants and the concentration of products is equal to 1, right. So, these are the two important graphs that shows the equilibrium state, right. Next, so this is the equilibrium state, from the equilibrium state we can understand more, we can draw the more conclusions, that is at equilibrium, this is the equilibrium, this is single line indicates when we plot the graph between time versus rate of reaction, this is single line where the rate of forward reaction is equal to rate of backward reaction, and this single line indicates the equilibrium, because at equilibrium the rate of forward reaction is equal to rate of backward reaction. So, this is the equilibrium. So, at this equilibrium, the physical properties like density, viscosity, surface tension, color, etc., whatever the physical properties does not undergo change, okay. At equilibrium state, physical properties like density, surface tension, viscosity, color does not change with time, right, okay. So, the equilibrium and the equilibrium has, and if you add the catalyst has no effect on the equilibrium, because if that reversible reaction is being catalyzed by some catalyst, that catalyst does not affect the equilibrium, because catalyst is a foreign substance which accelerates the rate of reaction. So, rate of forward reaction as well as rate of backward reaction. So, catalyst has no effect on equilibrium, right, and at equilibrium physical properties does not undergo change, right. So, and one more important point is at equilibrium rate of forward reaction is equal to rate of backward reaction, physical properties does not undergo change, right. And one more important point is that at equilibrium, already I told you, equilibrium is established in reversible reactions, and in that reversible reactions tug of war takes place. In the tug of war game, one group is pulling with a certain force and other group pulling with the same force. Whenever the forces of these two groups are equal, there exists a equilibrium between the two groups, okay. That means in that tug of war game, like in the tug of war game, this group, the group in this side is always pulling in this side, and other group always trying to pull that to that side. So, that group is trying to pulling in that direction, and this group is try to pull in this direction. So, whenever the forces of the two groups are equal, equilibrium is established. But till if the equilibrium, though the equilibrium is established, the two groups are trying to pulling. So equilibrium is dynamic in nature. Okay, equilibrium is dynamic in nature, right? So equilibrium is dynamic in nature, because after the establishment of equilibrium also, the rate of forward reaction and backward reaction continue to takes place. They continue to takes place even though equilibrium is established. That's why equilibrium is dynamic in nature, and catalyst has no effect on equilibrium. And coming to the characteristics of equilibrium constant, its value is independent on the initial concentration of reactants, and its value predicts the direction of the reaction. Its value predicts the extent of reaction. And one more important point is its value, equilibrium constant, allows us to determine the equilibrium concentrations of the products and reactants. So if we know the if equilibrium constant, if we know the equilibrium constant is concentration of products to concentration of reactants. If we know the for example, if you take let us consider the reversible reaction, A moles of A, B moles of B, reversible reaction C moles of C and D moles of D. So for this we can write the equilibrium constant as C moles of C, that is concentration C power D and D power D, by concentration of A power A and concentration of B power B. Okay, if we know the equilibrium constant and if you know this concentration, then we can calculate the equilibrium concentration of D. Okay, if we know the 4 terms in that equation, we can get the value of another species concentration. Okay, so equilibrium constant that predicts the direction of the reaction. Okay, that predicts the direction of the reaction and that predicts the extent of reaction, and with the use of equilibrium constant we can find the equilibrium concentrations, right? Now we shall go through the Lechateliar's principle. Right. Now we shall go through the Lechateliar's principle. Lechateliar principle. Right. So Lechateliar principle is exclusively applicable to most often we understand we can apply the Lechateliar principle to reversible reactions. Okay, so let us go through the statement of Lechateliar principle. Right, if a chemical reaction at equilibrium is subjected to change in temperature, pressure or concentration, then the equilibrium shifts in the direction in which change is nullified or reduced. I repeat, Lechateliar principle statement is, if a chemical reaction at equilibrium is subjected to change in temperature, pressure or concentration of species, then equilibrium shifts in the direction in which change is nullified or reduced. Right, and I thought that I think summary of Lechateliar principle is enough to understand rather than its elaborative explanation, because elaborate explanation does not give you any advantage, but when we go through the problems then it gives an advantage, right. So that's why I decided to give the summary of Lechateliar principle. Okay, I shall give you the summary of Lechateliar principle, right. So let us consider the general reversible reaction, that is A moles of A plus B moles of B. This is a reversible reaction, okay, and it forms C moles of C and D moles of D. Okay, this is the general reversible reaction. Okay, so what is Lechateliar principle states that if a chemical reaction at equilibrium, this is the reaction this is the reaction, reversible reaction where equilibrium is established. So if a chemical reaction at equilibrium is subjected to change in temperature, pressure or concentration, then the equilibrium shifts in the direction in which the change is reduced or nullified, right. So let us see the what is the effect of temperature, what is the effect of pressure, what is the effect of concentration. So now let us go through the first let us go through the temperature effect. Temperature effect. Okay, if temperature effect, if the temperature of the reaction mixture is increases, if we increase the temperature of the reaction mixture, then equilibrium shifts in the direction of endothermic reaction, right. Already I told you what is that what Lechateliar principle states, if we change, that is if a chemical reaction at equilibrium is subjected to change in temperature, pressure or concentration, then the equilibrium shifts in the direction in which change is nullified or reduced. Here we are increasing the temperature of the reaction mixture, increasing the temperature of the reaction mixture. If we increase the temperature of the reaction mixture, then equilibrium shifts in the direction of endothermic reaction, that is the direction in which heat is absorbed, because we are increasing the temperature. So to escape from that high temperature, equilibrium shifts in the direction of endothermic reaction, that is in the direction in which heat is absorbed, right. So when temperature is increases, when the temperature of the equilibrium is increases, equilibrium shifts in the direction of what is it called, endothermic reaction. Endothermic reaction, equilibrium shifts in the direction of endothermic reaction, right. And what happens when we decrease the temperature of reaction mixture? If we decrease the temperature of the reaction mixture, then equilibrium shifts in the direction of exothermic reaction, shifts in the direction of exothermic reaction, that is the direction in which heat liberates. So if we increase the temperature of the reaction mixture, then equilibrium shifts in the direction of endothermic, and if we decrease the temperature of the reaction mixture, then equilibrium shifts in the direction of exothermic reaction. That is the effect of temperature on equilibrium state. Next, let us go through the temperature, pressure. If we increase the pressure on the reaction, if we increase the pressure on the reaction, then equilibrium shifts in the direction of decrease in volume. If we increase the pressure of the reaction, that then equilibrium shifts in the direction of decrease in volume or decrease in number of molecules, right. If we increase the pressure of the reaction or if we increase the pressure on equilibrium, then equilibrium shifts in the direction of decrease in volume. So equilibrium shifts in the direction decrease in volume, because we are increasing the pressure, so when volume is decreases okay, so when pressure is increases, to nullify that extra pressure, volume is decreases. Okay. Okay, so if we increase pressure on the reaction, then equilibrium shifts in the direction of decrease in volume or decrease in number of molecules, right? And if we decrease the pressure on the reaction, then equilibrium shifts in the direction of increase in volume, when pressure decreases, when we decrease the pressure on the reaction, then equilibrium shifts in the direction of increase in volume or increase in the number of molecules, right? Next, and third one is concentration. Concentration. Okay, let us see what happens when we increase the concentration of reactants, right? So when we increase the concentration of reactants, here the concentration of reactants, when we increase the concentration of reactants, what happens when we increase the concentration of reactants, then equilibrium shifts in the direction of forward reaction. We are increasing the concentration, so to overcome or to nullify, to reduce that extra increased concentration, reaction proceeds in the forward direction. So with increasing the concentration of reactants, equilibrium shifts in the direction of forward reaction. Okay, and if we decrease the concentration of reactants, okay, so here the concentration of reactants are decreasing. Okay, so equilibrium shifts in the direction of backward reaction. Okay, so equilibrium shifts in the direction of backward reaction. Okay, and one more important point is, if we increase the concentration of products, then equilibrium shifts in the direction of forward reaction. And if we decrease the concentration of if we increase the concentration of products, then equilibrium shifts in the direction of backward reaction, right? And if we decrease the concentration of products, okay, so if we decrease the concentration of products, then equilibrium shifts in the direction of forward reaction, vice versa. Okay, and one more important point. Next, addition of inert gas. Okay, so addition of inert gas, this happens only in the case of if the reversible reaction is gaseous reaction, that is that happens in the gaseous molecules. Okay, if addition of inert gas on equilibrium, okay, it depends on the effect of addition of inert gas, depends on the conditions of the equilibrium and type of reaction, right? For example, in this gaseous reaction, delta N is equal to 0, that is number of moles of gaseous products minus number of moles of gaseous reactants is equal to 0. So delta N means, that is number of moles of gaseous products minus number of moles of gaseous reactants. If the delta n is equal to 0, then addition of inert gas has no effect on equilibrium at no effect on equilibrium at constant volume and at constant pressure. Okay. So, if delta n is equal to 0, then addition of inert gas at equilibrium, that has no effect on equilibrium at constant volume and at constant pressure. When we concerns with gaseous reactions, we need to study the reaction at constant volume and constant pressure. So, at constant volume and at constant pressure, there is no effect of effect on addition of inert gas to the reaction, right. If delta n is equal to positive, then addition of inert gas has no effect at constant volume, but at constant volume, addition of inert gas has no effect on equilibrium, but at constant pressure, equilibrium shifts in the direction of right side, that is forward reaction. So, right side means already we know that equilibrium reversible reaction takes place in the two directions, that is left to right and right to left. Okay. So, equilibrium shifts in the direction of right, that is from left to right, that is a forward reaction. So, equilibrium shifts in the direction of forward reaction, only it happens at if delta n is equal to positive and at constant pressure, equilibrium shifts in the direction of forward reaction. Okay, that is a right side. Okay, right side. And if delta n is equal to negative, that is number of moles of gaseous products minus number of moles of gaseous reactants is equal to negative, then there is no effect at constant volume. Already I told you, when we concerns with gases, we need to study the reactions at a constant volume and at constant pressure. So, at constant pressure, there is no effect on equilibrium, there is no effect, addition of inert gas on equilibrium has no effect on equilibrium, but at a constant pressure, equilibrium shifts in the direction of left, that is backward reaction, left. Equilibrium shifts in the direction of left side, that is backward reaction. Okay, but at constant volume it has no effect. One thing that you should remember in your mind is that when delta n is equal to positive and delta n is equal to negative, at a constant volume there is no change, there is no effect on equilibrium by the addition of inert gas. Okay, this point should be keep in your mind. Okay, because at a constant volume, whether it is delta n is positive or delta n is equal to negative, there is no effect on equilibrium by the addition of inert gas. I hope you all understand this Lechateliar principle, and I thought that elaborate explanation of Lechateliar principle does not give you any advantage, but when we go through the problems, when we go through the more number of problems, that enables us to understand, that gives a sound understanding the concept. Okay. So, in the next video I shall come up with problems on equilibrium constant. Thank you.